Okay, good. So let me start. Right, so the title of this talk is Yes, there's an Oblivious RAM lower bound, which sounds like there was a question, and I'll get to the question later on in the talk. And this is joint work with Jesper Buus Nielsen, who is a professor in Aarhus University in the crypto group. Okay. So what's an Oblivious RAM? So an Oblivious RAM was introduced in 1996 by Goldreich and Ostrowski. And what is the idea? The idea is that you have some sort of, you have an algorithm that runs on a random access machine. And what you want to do is you want to somehow encrypt the memory access pattern of your algorithm. Okay, so let me try to motivate it a bit. So imagine that you want to run a program on a computational device with limited memory. But what you have is like a large server where you can put your data, but maybe you don't trust this server. So what you could do is you could try to, you could encrypt the data, of course, so the server, by looking at the data, cannot learn what it is that you're storing. But maybe you also want to run some sort of algorithm on your data while it's sitting at the server. For instance, you could imagine, like, let's say I have a graph that I'm storing on my server, and maybe I want to run a breadth-first search on my graph. And even though, so maybe I can just encrypt every memory word at the server, but if the server looks at what I'm doing, the memory accesses of my breadth-first search algorithm, it could actually learn something about the graph that I had as input, right? If you think about what a breadth-first search does, it's quite obvious that you can deduce something from the memory access pattern. So the idea here is that you want to be able to take any RAM algorithm and then somehow transform it into another one where the server cannot learn anything by observing the access pattern. Okay. So here we don't really care about the server looking at the contents of what you're storing, because we can always handle that with like normal encryption techniques. So it's just the access pattern that we want to obfuscate. Okay. So basically the setup is that you have the server where you put the data at the server, and then there's someone, an eavesdropper, that looks at your access pattern, but not your actual data. And the requirement is that this eavesdropper is not allowed to learn anything about your input based on the access pattern. Okay. And more formally, if you have two sequences of accesses to your data of the same length, then the eavesdropper cannot distinguish the two sequences. Okay. So here's basically like a picture of the setup. So your CPU here is your client. You have a small memory available. It's not big enough to store all your data. The data that you want to store is, you can think of it as an array of n entries. This is the normal RAM of the program you're simulating. But what you have to do is you have to actually store it somewhere at the server memory. You might actually use more memory over here than you did down there, as there's no restrictions saying that you cannot blow up the memory usage. So you have an array, you want to represent it. What you want to support on this array is just write operations and read operations. Okay? And the way you support them is that each read or write will be translated into some number of probes into the server memory. Okay. So here I chose probes just to distinguish a read and a write from what's happening at the server, and also because we're going to use cell probe techniques to prove lower bounds. So this is the server memory. It's divided into cells. The input is an array with entries. So cells is the actual representation, and entries is just the input, the array that you're representing. Okay.
The CPU only has the client memory?
The CPU only has the client memory here, yeah. And gets the operations one at a time.
But the input is?
But you store it, like let's say initially the array is all zeros, and then you process some sequence of reads and writes, and you do that by making probes into the memory, so you're representing it here. So this is basically your data structure, and this is just your input that you're representing. Okay. Okay. And what the eavesdropper sees is just this sequence of accesses, right? So what are the addresses of the cells that I probe at the server? Okay. And the goal is that the eavesdropper cannot learn anything about what are the reads and writes that I'm performing. Okay. So there's a naive solution to this. Does anyone see the naive solution if I have a RAM algorithm? How can I make it oblivious?
Just query every cell every time?
Yeah, just query everything every single time, right? And so then you learn nothing by observing the access pattern, right? But that's, of course, a huge overhead. It's a linear overhead. So we want to do better than that. And so here's like the main performance metric that we care about. It's the bandwidth overhead, which is just how much extra do I have to read in order to obfuscate the memory access pattern. So more technically, if I'm simulating n accesses to a random access memory, and I do that by making m probes at the server, then the bandwidth overhead is the following. So if you go back to the slide here, so the input has R bits in every cell, and the server has W bits in every cell. So they don't need to be the same. In most natural cases, they're the same, but there's some upper bounds that have different parameters that only work when they're not the same. So here we included them as separate parameters. So basically, like the minimum possible number of bits that needs to be read, if I'm doing n accesses and each array entry has R bits, is NR. And how many do I actually read? Well, I read MW bits. Okay, so the overhead is MW over NR. That's how much extra I have to access in order to obfuscate what I'm doing. Okay, so there are a bunch of upper bounds already in the original paper. They prove that you can actually do it with the polylogarithmic overhead. I think maybe log cubed n or something like this. And there's a whole bunch of different suggestions for these ORAMs with different parameters. Some have a very large client memory and then they can still perform well. But what they seem to care the most about is when the client memory is just like a constant number of words, of these machine words. The best sort of up to very recently was this path ORAM from 2013, where you can get an overhead of log n if the cells at the server have log n bits and the cells of the input have log squared n bits. So it's sort of, that's why I have the separate parameters. It doesn't work if they're both log n. Okay. And then at this year's Fox, there's an improvement that gets log n, log n, when the word size in both settings are log n. Okay, so the most natural setting, I would say. Okay. So it's almost down to log n. Of course, you could ask, what about lower bounds for this problem? So in the original paper where they introduced the problem, they prove a log n lower bound. Okay. So what is the model for the lower bound? I think it's a model that most of you would not like in this audience. So basically, they say that your algorithm is a balls and bins algorithm. Okay, so the only thing the server can do when you want to store a memory cell, you just treat it as an atomic unit and put it in some location. So the only thing you can do is shuffle things around. You cannot do, like you cannot sort of do XOR tricks on different things. You cannot sort of apply an error correcting code to the data that you're storing. And one could imagine that stuff like that could help to hide what you're doing, right? Do some sort of error correcting code or XOR tricks. So their lower bound only holds if you do not do such things, right? So you just have to move things around in atomic units. It also holds only if you have to be secure against an adversary with unbounded computation time. So it means that basically maybe you can break this log n barrier by using some sort of crypto assumption that factoring is hard, and based on this assumption you can do better. Okay, so that was still a possibility after their lower bound. Okay. One positive thing about this lower bound is that it holds also for what is called an offline ORAM. So this means that the lower bound holds even if the client knows the entire sequence of operations that it wants to perform ahead of time. So it can look at the entire thing and then decide how am I going to perform my accesses to the memory. Okay, so in that sense it's a strong lower bound because it holds for these offline algorithms as well. Okay, so that's sort of the state of affairs. And then, 30 years passed and nothing happened to this lower bound until 2016 when someone asked, is there really an Oblivious RAM lower bound? Right? So this is the question that we answer in our paper. Right? So what they did here was that they revisited this old lower bound and pointed out these caveats with the lower bound, the problems here, and then they proved something that would suggest that it's going to be very, very difficult to strengthen the previous lower bound. Okay. So what they show is that, so assume there is a sorting circuit, a circuit that can sort integers with W bits each, and that circuit has size little of NW log n. Okay, so you can get NW log n by running some sort of like a merge sort or whatever. Right, so assume you can do better than that. Then you can use that to get one of these offline ORAMs which breaks the log n barrier. Okay. So what does it mean? So it means that if I somehow manage to strengthen their lower bound so that it still holds in the offline setting, but it also holds if you're allowed to do bit tricks, then I would also prove a lower bound of NW log n on the circuit's complexity of sorting, right? And of course, we don't have any such lower bound. We don't even have anything beyond NW, right, the size of the input. So you would get like a superlinear circuit lower bound if you could strengthen this lower bound to bit tricks as well. Okay, so it's not saying that probably the lower bound is false. That's not what it's saying. It's just saying that it's probably going to be hard to prove the lower bound. What they suggested instead is, what if we drop this offline restriction? So what if we want to prove lower bounds only for online ORAMs? What's an online ORAM? An online ORAM is one where you do not know the sequence of operations in advance, right? So they just arrive to you one at a time. Now you have to do a read. Now you have to do a write. And anyways, if you think about applications, this is always what you need, right? If I want to run a breadth-first search, I don't know in advance, unless I know the entire graph, I don't know in advance what operations I'm going to perform. Right? And the whole idea was that the data was too big to store it locally, so for most applications, this is what I need anyways. So you could try to drop this offline assumption. And that's what we do. So our work proves lower bounds for arbitrary algorithms, so they're allowed to do all the bit tricks you like, just to any representation. And we also strengthen this assumption here, so it doesn't hold only against unbounded computation time adversaries. It holds even if you just require that no polynomial time adversary can distinguish two sequences. It's really quite interesting that we can prove lower bounds against such, crypto assumption will not help you. That's basically what we can prove here. And of course, then we drop the offline setting, so now the lower bound holds only for online ORAMs. Okay. So the setup now is just these reads and write requests come one at a time. And this is what you need in applications anyways. And all the upper bounds also work in the online setting. Okay. So just back, this was just a setup again. Now going to give you the ideas of the proof. Array, probes, the memory, and the client memory.
The lower bound is log n.
Didn't I say? Yes, we take the same log n lower bound from before and prove it again under these assumptions. Okay. So let's just look at the simplest case. Let's say there's no client memory, just to give the idea of the proof. And let's say we have this perfect oblivious, and it's again that even with unbounded computation time, you cannot distinguish the two, just to start out in an easy setting. And let's say the size of these entries is the same, just to fix things.
Does it matter how large R and W are as a function of
the lower bound holds for any R and W, no matter the trade-off between them.
So you're not getting the business of perfect oblivious. So what are you proving that?
And I'm proving the lower bound under the assumption that your ORAM is secure also against someone who has unbounded computation time to distinguish two sequences.
The original RAM that you're trying to encode.
Say again?
The original program is secure.
Yeah, I'm going to say that even if this eavesdropper here that looks at the access pattern, if she has unbounded computation time, I'm assuming that even if she has unbounded computation time, she cannot distinguish them.
Okay. That's great.
It's better if I can prove it when she has a lower bound, even if she just has polynomial time.
I don't understand this. In more sense, it would be better.
So the lower bound. So what I'm saying is, if I
prove it even for adversary that can do this, no, it's really better.
no.
If you can build an ORAM against information which is information theoretically secure, it's better than building one which is cryptographically secure.
Yes.
Yeah.
So he's proving that you cannot build one. So
You can't even build a cryptograph system.
Oh, okay.
Okay. So I'm going to define like a hard sequence of operations, and then we're going to analyze it. So the hard sequence of here's one sequence of operations. I'm not going to claim this is the hard one, but what am I doing here? So think of this as time, from left to right. And then in the beginning, I'm just going to, in the first array entry, I'm going to write some piece of data R1. R1 is just going to be odd random bits. And then I'm going to write to the second entry, the third entry, and so on. And I'm going to do that n half times, and then I'm just going to read them off again, one by one. So then you can ask the following question. So look at this sequence of operations and split them into two halves, the first half and the second half. Then I'm going to ask, so when I process this sequence of read operations over here, how many cells would I need to read that were written in this part? Does the question make sense? So I'm counting how many times will I have to access something that was written over there. Does anyone see what do you think in this case?
At least n over 2.
Yeah, at least n over 2, right? It's just too much entropy in some sense. In all, there's too many bits here. You need to read something that can tell you what those bits are. So just there's 8 of them. You have to read 8 cells just to transfer the bits. Okay. So where does this technique come from, where you sort of look at 2 consecutive intervals and count the number of probes that are happening? So this is taken from one of these old data structure lower-bound papers by Mihai Petrascu and Eric Demain. I think maybe it was even Mihai's first paper, where they prove log-n lower bounds for dynamic data structures. So maybe what we're going to do is we're going to try to use that technique. But of course, this technique will not do the trick alone, because basically what we're looking at is an array problem, right? Read and write. And an array problem has a very efficient solution if you're not required to be oblivious, right? So this technique, so if you're not trying to exploit the obliviousness, then we're not going to get a log-n lower bound. So we need to do something more. And the trick here is, so now let's change to this dummy sequence of operations. This is another sequence than before. It just, every single operation, the first half is just write to entry 0, you just write the all 0s bit string, and then you just do that n half times, and then you just read entry 0 n half times. Make sense? So now the question is, for this red sequence operation, this dummy sequence, how many probes will there have to be between the first half and the last half?
So oblivious is 8.
It has to be 8, right? Because otherwise, the eavesdropper can distinguish the 2 sequences, right? So the eavesdropper, because she sees the access pattern, so she can just count how many times is the second half accessing something that was written in the first half. So she just looks at this access sequence and checks, was there 8 probes or not? And if you probe less than 8 things over here, she could distinguish the 2 sequences. So for this dummy sequence, there will also have to be 8 probes that are made by the second half of the reads into what was written during the first half of all these writes. Make sense so far? And now we're going to do what Mihai and Eric did. We're going to look at different sizes of these intervals. But this time, now I'm going to look at a different distribution over sequences. Right, so now I'm going to do 4 writes, 4 reads, 4 writes, 4 reads. And now I can now look at the first half here and look at how many times will these reads have to access something that was last written over here. And I guess by the argument as before, you have to access 4 things, right? Because there's just so many bits you need to transfer. And now you do the same here, because this was after everything that was done here. Accessing stuff that came before, that was accessed before, doesn't help you, right? Because there's just not enough. There's no information in everything that was done up to here to help you answer these read operations. So therefore, there has to be a lot of operations in this subinterval that access something that was last written in that subinterval. You can put a 4 up there as well. And now here's the trick, because now we go back to the same dummy sequence. Right? This is using the obliviousness. You're not allowed to distinguish the 2. So for the dummy sequence, the same thing has to hold. The operations in this half here, even though these are all reads, there's no information there, but to hide the access pattern, you have to still access something over there. Otherwise, you could distinguish yourself from the previous sequence. And the observation, which was also in this original paper by Mihai and Eric, is that all these probes that you count in this way are all distinct. Because any single probe that your algorithm does will only in some sense belong to one of these sets, right? There is some sort of unique last time the cell was accessed, and you're going to be counted at the lowest common ancestor of those 2 nodes. So what you can do is, for this red sequence, if I want to know how many probes are there in total, I just sum up all the probes in all these nodes. Makes sense? So I can do another layer. Now I have even smaller intervals, and I can get these 2, 2, 2, 2, 2. What you see is I get this very nice binary tree. And all that's left now is just to sum up everything in the tree.
Sorry,
Yeah.
so you're saying you are hiding that those probes are read
Yeah.
as opposed to write.
Yeah.
Okay, so you also want to hide that.
Yeah, basically, I'm hiding that I'm not that I want to make sure that you cannot distinguish the red sequence from this one.
Okay, even though you're switching from read to write.
Yeah, yeah, exactly. I have to still do. Here I have just by here. There's no obliviousness. I'm just saying there's just so much information that I have to access a lot to get to recover the information. And here I'm saying, but I have to be indistinguishable from that one. So I also have to do the same thing here. And I guess you see where the lower bound is, right? The sequence had length n. There's n half here. They sum to n half at this level. They sum to n half at this level, and n half here. The height is log n, so you get an n log n lower bound on the total number of axes. Okay. Which means that the overhead is log n. And if you want to consider different parameters R and W that are not the same, then you just realize that at every level you had to recover all the bits. There's NR bits that requires NR over W probes. And if you look at the overhead, it turns out that they cancel out and it's still a log n overhead, regardless of the parameters. Okay, then there was this client memory, because we assumed there was no memory. The client memory is easy to deal with just at an intuitive level. So let's say the client memory can hold has room for two elements. In some sense, you can just transfer, you can keep two of the things in memory when you go from the one half of intervals to the other half, to the next interval. Okay, so we can prove this formally, but I think the intuition makes sense, right? The client memory cannot hold more than two items, so most of the stuff you still have to do probes to recover.
So these 1 minus 2s I should just ignore?
Yeah, so just ignore the bottom log n plus 1 levels. Everything above has at least half of the weight it had before, so it's n over 4 per level at least. And so basically now, if you sum everything up, you basically get this lower bound, and it's just a log n over m lower bound. So it actually shows that even if you allow very large client memory up to n to the 1 minus epsilon, you still get a log n lower bound. Okay. Let me just give you the last, I just have a few minutes left. The last case is, what if you want, now you have this computational indistinguishability, like you have against a polynomial time adversary. I guess if you think about it, what the eavesdropper was doing was just, it was a long way back, was just counting these probes and these intervals, right? She was just counting. And that's something she can do in polynomial time. She just counts. So already she's doing it in polynomial time. What you can say is, what if she's allowed to, what if we only require that she's not allowed to distinguish them with probability 1 over 4 or something like this? There's some slack there. And basically the same type of proof goes through. So you start by proving a lower bound, saying under this random distribution that it's very likely that you have to probe a linear number of things. Like, so with probability half, you have to read k over 4 things if the interval has length k. Something like this makes sense, right? It makes sense that you almost always have to read everything. You can prove this like with an encoding argument. And that means that the expected number of probes under the red sequence also has to be omega k. This follows just by Markov's inequality, right? Because if it was less, then the probability of seeing k over 4 is no more than a quarter, which means you can just check, was there more than k over 4? In the first sequence, the blue sequence, this happened with probability at least a half. And if this was not true, it would happen with probability at most a quarter, so that there's this quarter gap that you can use to distinguish the two sequences with probability at least a quarter. Okay. And then, so now it's just expected number of probes, and fortunately we use linearity of expectation and just sum it all up. And, and then again, we just have to sum everything that's above a certain level to deal with the memory. But that's actually the full proof. Yeah. So the lower bound is log n over m, even if you just wanted to hold against these polynomial time bounded adversaries. And also, we extend the proof to hold also if you allow randomization. So whenever you answer a read, you're allowed to fail with some constant probability. The lower bound still holds, even in this case. So basically, there's nothing you can really do to break the lower bound. Okay, so this is just like a summary of everything that has been done. So there were these previous upper bounds. Here's a little bit more detail. If you had word size, they had this path ORAM that had an optimal overhead of log n, but only for sort of strange parameters. But it is tight according to our lower bound, because the lower bound holds for all parameters R and W. If you wanted both of them to be log n, they didn't quite get there. There was this panorama from this year's Fox that gets log n, log n. And now we prove that the lower bound has to be, there's a log n lower bound. There's still a tiny gap, but actually after our work, there was something published on, I think the ePrint, that you can actually get the optimal. You can get a log n overhead with word size, both W and R being log n. Okay, so suddenly in the last 2 years, there was this paper that questioned the optimality, and then suddenly everything got solved. Not inspired by our proof, but it's just, yeah, quite a fortunate thing. After 30 years, everything happens in a couple of months. But that's sort of the state here. There's one open problem that I think is interesting here is something. What if you just want to store your data as sort of like a read-only data? You don't want to change the data that you're storing at the server. So maybe in some sort of pre-processing phase, you know all the data. Now you're going to ship it to the server, and then later on you can query it. But you cannot. You have no write operation. You only have read operations. Okay. The best outbound is still log n, but can you prove this is a lower bound? Can you prove that if you don't just have reads only, there's a log n lower bound? You can fairly easily prove it if you require that you're not allowed to change what's stored at the server while doing your read operations. Then you can prove the log n lower bound. But actually, here you have the problem is that you have a client memory that may change between operations, and you can also sort of modify what's stored at the server. Maybe try to move some things around. You're just not doing write operations, but you can still modify the representation to hide your access pattern. I think this is an interesting open problem in this area. Okay, I think that's it.
So the eavesdropper counts. What if she cannot count?
If she cannot,
If she's in AC0.
it's a good question. I don't know. I don't think the
Probabilistic counting.
Yeah, probabilistic counting. I don't know. I am not sure. What can you do? I'm not a circuit complexity expert. But what can you do in? I guess you just need to count within a constant factor. That's enough for you here, I suppose.
You can distinguish strings that have like an overwhelming majority of ones versus an overwhelming majority of zeros.
Yeah.
Is that enough?
Right. I guess you just need. I guess in the reduction, you sort of just have to distinguish. In one case, we know there has to be a linear number of axes, and just has to distinguish that from a constant factor smaller. I think that probably she can do that. Yeah.
But I think I missed the main thing in the bound. So you started with the sequence of actually the writes, and you make the argument that the read have to read cells from the screen. That's clear. Then also a sequence of reads should be. And then how does that? Where does it help you to go to a sequence of reads?
Yeah, so the point of this fixed read sequence is that we can. The problem is that for any fixed distribution over these reads and writes, if I have some distribution over reads and writes, there's so on the blue distribution, right? There's we don't use the obliviousness yet, so it's just a data structure, and there you can do a linear time. You just read and write what you're doing, right?
Yes.
What we use the red one for is, in some sense, to collect all these different, sometimes we can change the underlying distribution to log in different distributions that all of them must have probes in different locations. And then we can argue that there's one fixed one that should do the same as all these log in different ones. I think that's the role of this red sequence, is that we can somehow look at many different blue distributions that yield probes in different time spans in some sense. And then you have to be indistinguishable from all of them, so you have to do all the work that all these blue things did in order to. That's sort of the role of. There's one fixed sequence that's you have to hide against all the other ones. I think that's so you can collect all the lower bounds in some sense. I think that's the intuition, at least.
How is the open problem different than proving lower bound for the offline? What is the difference between still a static file, right? You pre-process and then they're read-only queries, right?
Yeah, but you don't know the sequence of reads in advance. You still have to, it still has to work even if you don't know the sequence of reads in advance. But they arrive to you in an online setting, the sequence of.
That's isn't it the same as static, the offline pre-process, and then I need to prepare for all?
No, but there you, in the offline setting, you know the entire sequence of reads.
Including the...
Yeah, you know everything you're going to do, and then you can, decide something based on the whole sequence. I know that first I'm going to read number 17, then I'm going to read number 3, then I'm going to read number 5.
I thought somehow that even for that setup, what you mentioned, I thought there was a follow-up paper by Ricks et al. That showed that even for your open problem, if you do something, you get new LDC there.
Oh yeah, there's something in those lines, but it's only for strange parameters that they get something. It's only like...
I thought it was even for linear space, if you prove...
Yeah, but there's something, the word size has to be log cubed in or something weird. It's not quite the same range parameters. I think there's something you can do if you don't look at the bandwidth overhead. I think their solution has a small bandwidth overhead, but you make many probes. It's something with having this W and R be quite different as far as I remember, like be logarithmically different as far as I remember. So there's still room to prove that you have to do log n excesses. Maybe not the bandwidth overhead being log n, but maybe log n excesses would make sense in this case. Yeah.
So, did I read wrong? It looked like you were dividing by W in your lower bound.
Yes.
Yeah, so if the word size is log squared, do you get anything?
If the word size is log squared and R is log n.
Yeah.
Yeah, no, then we...
like log n times R over W, so that would be like constant.
Yeah, but it's still the best you could hope to do would be sub-constant on average, right? The amortized could be less.
I guess what I'm saying is their overhead for like W squared, R equals W squared, could be improved to constant in principle.
So intuitively, their overhead could be made even smaller, yeah. Right, so the minimum is this, right, so what are we saying? So the best you can hope for, right, is NR over W. And if W is large, this is sublinear, so amortized could be sublinear, and it's still, the low bound still says it has to be a log n factor bigger than this.
Yeah.
Right, so,
Yeah.
so in some sense it's still strong, you still cannot do the best you could hope for. Right?
Yeah, I guess I'm saying for their parameters, is it true that you could make the bandwidth constant?
No, if you plug them in, no, their overhead is computed, in this one, the overhead is computed as this, using this formula NW.
Sorry, I'm kidding.
Yeah.
I see.
Yeah. Okay, then let's stop.
Thanks, figure it out.